Here we have a problem from the LA City College 2008 math contest, and it's a bit of a physics-inspired problem today, which is actually pretty coincidental because I'm going to be getting into physics course content on the channel pretty soon. Look out for those in the afternoons if you're interested. So here we have a circuit as shown, and our goal is to get from vertex A to vertex C on this circuit. But each of these switches have a probability P of being closed and 1 minus P of being open. And the problem asks us to find the probability of getting from vertex A to vertex C, or the current getting from vertex A to vertex C, I should say. So let's note that first of all, there's two possibilities here. We can go this way through vertex D, or we can go this way through vertex B. So I'll go ahead and write those here. This is where we'll work with the case where we go through vertex D, and this is the case where we go through vertex B. So let's go through D first. If we go this way, we have a P chance of this circuit being closed and a 1 minus P chance of it being open. So if we're going this way, we run into this switch first and then this switch second. And if the circuit is open at any time, we don't reach vertex C going in this orange direction. So both of these switches have to be closed, which means we're working with a probability of P squared here. Well, that's good. And now we can say the same thing for the green arrow because we also go through two switches here. We go through this switch here and this switch here. So this also has a probability of P squared of getting through. And so you might say, well, that's great. We have a probability of 2P squared because we have two different possibilities of getting from point A to point C on this circuit. But we're not quite done because what we're doing here by taking both of these and adding them together is overcounting one of these possibilities, which is where both directions, the green and the orange stars, both occur. And that occurs at P to the fourth. That's when all of these switches are closed. So I'll go ahead and write that here in the blue star. When all of the switches are closed, we have P to the fourth. And so we need to subtract this P to the fourth from these 2P squared. We need to take out the overcounting that we did from this orange star and this green star. But then we can simplify this really nicely and say that we have P squared times 2 minus P squared, like that, as our final probability for getting from vertex A to vertex C. Now what I want to do is take this problem and generalize it to an n amount of switches. So let's go ahead and redraw this circuit and I will start doing the math on that on the next board. So here I've drawn a linear circuit with n sides and n switches, where n equals 2k and k is a natural number. In other words, we're working with an even number of sides and switches. And the circuit looks like this, where k switches are on one side of the circuit and k switches are on the other side of the circuit. And we're trying to get from point A0 in the circuit to point AN. And I'll just draw a little reminder up here that our probability for each switch is P for being closed and 1 minus P for being open. So now to get from A0 to AN, we take P to the K, going with this green direction here. But then to take the orange direction, we have the exact same because we're working with K switches. So we have P to the K plus P to the K. But then we subtract all of the copies, which is minus P to the N, or P to the 2K here. Maybe I should write it as that. So those are all of our duplicates, but we can simplify this by saying 2P to the K minus P to the 2K. But that simplifies down to P to the K times 2 minus P to the K. So this is our general form when working with a circuit like this. I think it'd be pretty interesting to work on something like this that maybe has an odd number of switches or something like that. Similar, but a little bit different maybe in the future. Let me know down in the comments if you have a problem like that or if you can come up with one yourself. And that's enough for now.